We need to know what the work energy theorem is. The theorem goes that work done by a constant net force in displacing, in other words, moving an object, is equal to the change in kinetic energy of that object. So change in kinetic energy transferred is work done, which makes sense. So if there is a change in kinetic energy, it is the energy. Energy is force times distance, and force times distance is work done. So all of those things are equivalent to one another. Let's look at an example. So we've got a 4 kilogram block and it's sitting at rest and it's pulled to the right along a rough horizontal surface by a constant horizontal force of 12 newtons. The coefficient of dynamic friction, because it's moving, is 0,15. Using the work energy theorem, calculate, so in other words, you have no choice here. You have to use the work energy theorem because actually there are lots of other ways of doing this. You could easily say, work out just acceleration. You could say 12 divided by 4, you get the acceleration at 3, and then you can say that you started at 0 velocity, and you can work all of this information out without the work energy theorem. But one of the new things that they like to do is ask questions that they force you to use the work energy theorem. Anyway, it asks you to calculate the speed of the block after it has moved a certain distance. First thing I'm going to need to know is what is the frictional force, because although I'm applying a 12 Newton force, I have also obviously got some resistance to that motion, because here's the block. It's on a surface. I'm applying 12 newtons that way. There must be a frictional force going backwards. It's on the horizontal, so it's easy. Frictional force is equal to mu, the normal force. And if you are on a nice horizontal surface like this, the weight going down is exactly equal to the normal force. So we can take that as actually the normal force if you look at your information sheet. And it's 4 times 9,8. And 0,15, and multiply that all out. And so my frictional force turns out to be in the opposite direction over here, 5,88 newtons. So what is the net force or the resultant force? I do a subtraction. I then take the resultant force, multiply it by the distance through which we moved, and I am able to say that that's equal to the change in kinetic energy. This whole thing started off stationary, so my initial kinetic energy is 0. My kinetic energy at the end is equal to the mass of the object, half the mass of the object, and we've got a square of the final velocity. Once I have square rooted that, I land up with 3,03 meters per second. The other thing that they ask questions about, sort of at the tail end of questions around work, energy, and power, is the concept of efficiency. Efficiency is the ratio of your power input to your power output. In other words, how much power am I getting out versus how much power am I putting in? Input power comes straight off the sort of grid, for want of a better word. The power out is what work does it actually do. So this is my investment. In other words, what did I pay for to get in there? And the power out is the actual work done per unit time by machine in a unit time. And it's the smaller number over the bigger number. Obviously, your efficiency is never going to be more than 100%. You don't get more out of a machine. It's kind of like you don't get more out of the bank than you put into the bank. It just doesn't work like that. I suppose there's something called interest, but let's ignore that. Right, anyway, when the electric motor is connected to a 12-volt DC supply, it draws a current of 1,2 amps. So what have we got? We've got 1,2 amps and 12 volts. That is what the machine gets in from a 12-volt 1,2 amps. It has a power rating of 14,4 watts. What we now do is that's what the power rating is of the machine. The motor is now used to lift an object of mass 1,6 kilograms through a vertical height of 0,8 meters at a constant speed of 3 seconds. So what is work done? Work done is equal to the force times the distance. And what am I working against? I'm working against this mass, so it's 1,6, 9,8, because it's a weight that I'm working against. And so that's Fg. And I need to work that out. And the distance through which I move it is 0,8 meters. I do this in a time. Remember what power is? Power is work done divided by time. So I'm going to do it in a time of 3 seconds. Let's just work out this work done. So that's equal to 12,54, and it's 12,54 in 3 seconds, which means that I'm only actually getting power out of 4,18. Let me try and make this a little bit. Bring that over there. So I'm getting 4,18 watts out. When I put in 14,4 watts. They needn't have told me the 14,4, by the way. I might have had to have calculated that particular value by saying power is equal to V times I, and I would have gone 12 times 1,2, and I would have then got 14,4. So that is what I'm putting in, and I then go for efficiency is equal to what I got out divided by what I put in times by 100, and I land up with 8,2%. That's a very inefficient device, I must say.